Today we're going to look at one of the problems from our Codeforces problem. We're going to look at specific stack of presents. So to read the question, Santa has to send presents to the kids. He has a large stack of n presents numbered from 1 to n, the topmost present being number A1, the next present A2, and so on, and the bottom one have AN. All these numbers are supposed to be distinct. So Santa has to order m distinct presents he has to send, B1 to BM, and he'll send them in the order they appear in the list. So basically he's going to try to get out these presents from a stack of presents n. So to send a present, Santa has to find it in the stack by removing all presents above it, taking this present and returning all the removed presents from the top of the stack. So if there are k presents above the present Santa wants to take, it would take him 2k plus 1 second to do it. Fortunately, Santa can speed up the whole process. When he returns the present to the stack, he may reorder them as he wishes, only for those which are above the presents he wants to take. The presents below cannot be affected in any way. So we're asked for the minimum time required to send all the presents, provided that Santa knows the whole list of presents he has to send and reorders the presents optimally. Santa cannot change the order of presents or interact with the stack of presents in any other way. Your program has to send t different test cases. So the first line of input is going to be the number of test cases. The second line will be two integers, the number m and n, which is the number of presents in the stack n, and the number of presents in the list he sends m. So the second line is going to be from A1 up to AN, and the fourth line is going to be from B1 to BM, and the sum of all of them not exceed 10 raised to 5. So for example, let's open a new one and type up the example. Say A was a stack of, looking at the first example, 1 and 2, and B was 3, 2, and 1. So first of all, you try to remove present number 1, which is on top of the stack. So this would take him, let's call it time. It's going to take him 1 time to remove this element from over here, so he removes it. So second one is way around here, so there's one element before it, therefore using this formula right here, it's going to be plus 3, 1 plus 3, which is currently 4, and then this one's going to be removed. So when he's looking for 1, he's basically, it's up front, so it's going to take him 1 more second, which is equals to 5, which is our answer. But a more descriptive problem would be the second one. In this case, we're given an A of 2, 1, 7, 3, 4, 5, and 6, and a B, only 2 numbers, 3 and 1. So first of all, you try to remove 3, which is way over here. So 3 elements in front of it, you'd have to take out all these 3, which according to the formula, the time would be 7 seconds just to do that. So when he returns them, he can reorder them in a way, in this case 1, 7, 2, 4, 5, and 6. So that 1, which is our next number, is up front. So when they try to remove this one, it only takes 1 second. So added together, it would be 8. So that's the answer right there. So what we can do here is we look at the first element. So let's take this one out, and also this one. So what we do here is we hold the first number, then we can go through in the entire list, only stopping when we find our required number, which is 3. So we hold a pointer, we remember this location, and then we can apply the formula and add time 2 times 2. In this case, there are 3 elements, so plus 1. So in this case, we also then look for 1, and this we can call it our max travel. In this case, it would be, it went to index number 4, which is basically index number 3, which is right here. So when he looks for 1, it's going to be on the first index, which is the 0th, the first index. So it's going to be less than 3. So in this case, we just add 1. We go on like this for every number. If it's above the one we just searched, then it's going to be the whole thing, which is this formula we saw right here. It's going to be that. Otherwise, if it's less, we're just going to add 1. That's basically the way we're going about it. So first we need to take the inputs. We can call this test cases, and we can take the input from the user, and then after we have that input, we have 2 numbers, which is n and m. So we can just split that one. Then we need the entire list of a, which is we can turn them to integers while we're here. And also our b list. We're guaranteed that these are unique integers. We'll use that for in later. So we can print out the result of our, let's call, min time finder. We'll need a and b. Actually, that's all we need. So in this case, we'll just write our function min time finder, which is a and b. We can, since we're going to use them a lot, we can call this the stack of elements, and this the to be sent. And in this case, we want to go through all the elements in to be sent, so we want to also know their index. So in this case, we keep a track of 2 things: our max travel, and basically our current time. Max travel in this case, we haven't gone anywhere, and our time, which is currently 0. So now we go through, we want to find I, which is to be sent I will be our present to find. Be sent I. So we want to go through the entire A. A could be really large number, so we can do what we only care about if it's above our max travel. If it's below, then we don't care, we just add 1. If it's bigger than that, that's when we're concerned. So what we can do here is we could do found location. You can set that to 0 or -1 actually, for j in range len of our present stack. If stack j equals if it found the present, then our found location would be updated to j and would break. But if it doesn't find it, then it would still be -1. So if found location is equals to -1, since we're guaranteed it's supposed to be an A, we can assume it's before that, so our time would be added by 1. But if we did find it, then in this case what we want to do is take the length, how many elements there are before the number. So the number of elements before that number is going to be our found location. We're gonna add time. We're gonna add to time, so it's gonna be 2 times whatever the number of elements before it is, then plus 1. So here we found locations, how many elements there are before it, and we also removed I number of elements before it, I -1 to be precise, which is just to say we have removed I number of elements before we get to that location, before we get to that present to be sent. So in this case we add that amount, and in the end we want to return our time it took us. So okay, max travel, when do we update max travel? We update max travel if, in this case, so in this case we have traveled more than we previously did, so in this case we need to update our max travel to include our new found location. So I think this should work. Let's give it a try. Python 3, then I think Q3. So we have two test cases to try out, 3 and 3, and our first one's got 3, 1, and 2, and the next one is 3, 2, and 1. So in this case it's a -3, which was not what we expected. Mice found -I, -1. I think this is where we're having problems. -1 found is J. Just in case though. 7 and 2, 2, 1, 7, 3, 4, 5, and 6, 3, 1, 3, and 1, 4. Okay, don't know what went wrong here. So -1 -I. Do we have to include this? Okay, don't think we needed that, but I can't be sure yet. So I is the number of elements. Okay, I think should work now. 2 and 1. Okay, 3. This case is not what we wanted again. -1 -I. Okay, was it +1? Don't think so. So 7 and 2, 2, 1, 7, 3, 4, 5, and 6. And we want to take 3 and 1. 8, okay. This specific case, I don't know what went missing here. If found location is not -1, time +1, max travel. So max travel found location. Okay, what I want to do here is I want to print location, my found location, then my time, then my present. Okay, in this case 3 and 3, 3, 1 and 2, 3, 2 and 1. So found location is 0, that's our found location, and it's again 0, then it's 3. So in this case it's going to do I, in this case would be 0, so we'll do a 0 in this case. This would be 1, yeah. So by the next round we have a 1. Okay, then why are we, there was a 4 here and we returned 3. So don't know why. This should have returned, because this is 4, goes back again. It was supposed to be, okay, do we alter time? Nope, we just print it out. So okay, I want to print time. Two, 3, 3, 3, 1 and 2, 3, 2 and 1. So okay, this time was 4. Okay, in this case it decreased. Found location is okay. So what happened in this case was found location was actually lesser than the number we found. So in this case, okay, this was not from len. Okay, it's actually searching the entire list. Instead of searching the entire list, we want it to go from the maximum traveled all the way to the length. So in this case I think we'd avoid the error. So we have a 2, 3 and 3, 3, 1 and 2, 3, 2 and 1, 5 in this case. And on the second case we have 7 and a 2, 2, 1, 7, 3, 4, 5, 6, and 3 and a 1. So in this case it would be 8. Let's remove this. Also remove this. So okay, now, and let's remove this. So in this specific case, what we're looking at is the time complexity for every element in I. So if we say the n is supposed to be the length of stack, and m is the length of the list word of presents he wants to send. Then this would have big O of, because this is going through every element in M, which in the list of presents, which is OM, and we're going through the elements of the stack, but every time we reach to a new location, a new max, we found a new location, that the max is going to be updated, which is the starting point. So we're only going through the lists once. Once. So in this case, we're left with this. This is the time complexity we're using. No additional space is used, so memory is of 1. So that's where we are. Thank you.